Hi everyone, my name is Emnet, and today I'll be talking about initialization of non-negative pair fact 2 using independent component analysis. Me and Michael, we worked in this really interesting way of initializing non-negative pair fact 2, and we're really happy to share results with you. Starting with pair fact 2 is a tensor decomposition technique that has been used previously to extract quantitative signals from GCMS and GCGCMS data. However, the algorithm is generally solved multiple times for a single region using a randomly chosen initialization. Here in this presentation, we'll be talking about making pair fact 2 faster by using a single intelligently chosen initial guesses. Alternatively, what we hope to do is to create a parsimonious technique for handling GCGC TOFMS data. Everybody knows here there's a lot of problems with analyzing GCGC data. For example, you can get varying results depending on what data analysis parameter you use. The appealing thing about using pair fact 2 is there's really two parameters you need to input, and pair fact will take care of the rest. So you need a region of interest and you need the correct number of components, and then pair fact will spit out the information that you want. With Chromatoph, it isn't quite convenient. You need to put a lot of different parameters, and sometimes Chromatoph has less than the desirable consequences for the actual data. To illustrate some of the challenges with conventional data analysis in GC-GC TOFMS, consider these two cases. So on the left here, we see a toluene peak from the analysis of gasoline. The processing in this case was set up to capture signals from a small peaks, and the parameters were not appropriate for a very abundant peaks. Consequently, there were many false positive peaks as toluene that was split into 7 peaks instead of being reported as a single peak. And the other second problem is false negative on the right side, where a derivatized glycine peak that is clearly visible is not picked up by the integration software when it was 57 picogram derivatized glycine. These two types of problems with Chromatoph makes it difficult to identify the same thing across multiple samples. So we're choosing pair fact 2 because it's relatively simple and it's a nice machine learning technique, and we should expect to see fewer peak dropouts because based on how pair fact calculates, it calculates how much sample there is by using a regression of data and using known factors. So for example, elution profiles and mass spectrum. Here we have 3 algorithms. So we have pair fact 2, and then negative pair fact 2. Starting with pair fact is a technique for tensor decomposition that works on a 3-dimension to any dimension. But in the case of GCMS data, we have the 3-dimension that are retention time, mass spectra, and multiple samples. Pair fact decomposes the matrix directly, providing profiles of peaks and their mass spectra. The problem with pair fact is that it's too restrictive for real chromographic data, as it cannot account for a data where there are any shifts, for example, shifts in retention time. The second algorithm is the direct feeding algorithm, or the pair fact 2. Pair fact 2 is a tensor decomposition technique that again works on a 3-dimensional tensor. However, it allows data to shift 1 dimension from run to run. Consequently, if retention times are not perfectly aligned throughout the data set, it's not a problem. Pair fact 2 can still return mass spectrum and peak profiles that make sense. However, the problem with pair fact 2 is that the unique sample profile is calculated using singular value decomposition, or SVD. That means the profile themselves always must be orthogonal. And this orthogonality constraints don't always correlate with the latent chemical phenomena. You can see here in the right top here, the latent factor is close to each other in order to be orthogonal, and their shape is distorted a little bit. Also, there's a negative scores. And using a flexible pair fact 2, they are not distorted in the same way, and that's what we wanted for our data. So for our demonstration data set, what we've done is we've taken GC TOFMS data and we've unfolded it in such a way we can see a series of second dimension modulation, which corresponds to samples as with a normal GCMS experiment. GC TOFMS data presents itself as a series of cubes, and each cubes correspond as a sample. Each sample has I second dimension accusation, J mass channel, and K modulation. So what we did is we sort of stacked them on the top of each other to create a data set with a massive of replicants so that we can test the algorithm. Also here, in Dr. Heron's presentation, he will talk about a novel technique of decomposing a four-way tensor called pair factor by two. But just for this presentation, we just create artificially three-way data to test the different initialization strategies. So the calibration data or the sample of looks like this on GC. There's two components, derivatized adipic acid and salicylic acid. So again, here we'll be talking about the two different initialization strategies. One of them is random initialization, and the second is ICA, or independent component analysis initialization. Starting with random initialization, so what we did is we created a randomized solution profile. Then we tried to solve the model based on the initialization that we have and do the model solving 10 times. Once we have the initialization that sort of closest to our solution, or with the lowest sum of residual square. Once we have that, we sort of continue with that solution. Now with ICA, obviously random initialization takes longer. So for ICA, what we did is we sum all the samples together and our data to get a matrix. Once we have a matrix, then we use ICA to get the scores whose statistical independence is maximized and neutral information is minimized. And then once we have those scores, what we did is we use them as our initial estimates. So here, one point we need to emphasize is we don't need to initialize the mass spectra because the order in which the algorithm iterates, we calculate the mass spectra from the elution profile. But another technique that we can see here is we could have performed ICA on the transpose of the matrix or this cube, then we would be looking at the statistical independence and the mass spectra. But for this presentation and for this experiment, we're choosing a statistical independence and the elution profile. So using a data set, this figure shows ICA converges in a fewer iteration than randomized covectors. But it looks difficult to compare because randomized covectors, sometimes it will come up with a really good initialized guesses, and sometimes it will come up with a bad initialized guesses. So the standard for random initialization, as described by Hank and Rasmus Bro, who invented PairFact2, the best way is 10 random initialization, and each initialization goes to 80 times iteration. And then you pick the initialization with the lower sum of residual squares, and you allow that to go to convergence. And let's look at some of the results, what the results look like. So for this data set, we did both regular PairFact2 and then negative PairFact2. Just looking at the top here, we see the results from applying PairFact2 to the data. To the left, we see the extracted profile of the two compounds in red and blue. We can see that the retention times for each peak shift slightly from run to run. And then we can see that the extracted profile from the peaks for both low and high concentration. In the middle, we see the extracted mass spectra for adipic, derivatized adipic and salicylic acids compared to the library spectra, showing a good match quality. However, the sample loading right here shows some negative spikes, and that's the result of orthogonality constraint of PairFact2. We can also say that PairFact2 doesn't deal with peak dropout very well. So not every slice has a signal just because the way we unfolded the data. And here, below here, we see the results from application of non-negative PairFact2. We again see a reliable profiles. We see a reasonable mass spectra. However, the loading are all positive, which is as it should be for this data set. We then wanted to compare non-negative PairFact2 with random initialization and independent component analysis initialization. So we run the data processing again for both random and ICA initialization. Looking first at the results from random initialization, we found a result where the algorithm clearly failed to converge. Given the random starting point that it used, it just so happened this time that no sensible solution was found. The two factors or compounds that are not satisfactorily separated and the spectra match are much poorer, loading are correlated with positive and negative values. This is contrasted by ICA initialization, which yielded sensible results with the best library matches we've seen so far. Furthermore, performed this task about 8 times faster than PairFact2 with the random initialization. Here, in conclusion, so far we've compared 2 types of initialization on non-negative PairFact2, the ICA initialization and the random initialization. What we did is, when we did for ICA initialization, it took 500 seconds, and for random initialization, it took 4,000 seconds. From practical standpoint, when we were processing a data, getting the same input and obtaining the same answer, that always happened with ICA, whereas it didn't happen for random initialization. At the end, I would like to thank my group as well as the funding partners, NSERC, the Canadian Foundation and Innovation, as well as Genome Alberta, Genome Canada for funding this research, and all the nice member in this Zoom forum.